Hi guys, welcome to today's tutorial. We are going to look at some NCEA Level 2 Chemistry, continuing on some Le Chatelier principle questions. So these questions are very common in the exams, and I do have an old exam question at the end, which we'll go through together just to give you an idea, as a kind of like a summary to everything that we've done so far, which is the rates reaction, the Kc calculation, and as well as the Le Chatelier's principle. So just to start with some Le Chatelier's principle, so I verbally explained everything in my previous video, and then this one we are going to look at some wording, like how do we write it. Okay, so first question, like I have this equilibrium here, okay, and then the concentration of C was reduced, so that means C is reduced, and what is the effect on the concentration of B? Okay, so C is reduced, that means the equilibrium is no longer available, no longer there. So what does it do to minimize the change? It's going to favor the forward reaction to make more C's, therefore it's going to shift to the right, so you're going to use A and B to make more C's, so the concentration of B is going to decrease because you're going to use it. Okay, so if you look at the answers here, when the concentration of C was decreased, the equilibrium is no longer there. Alright, so the system will minimize the change by trying to increase the concentration of C. And how does it do it? You favor the forward reaction, so that makes more C's, so you use A and B to make more C, so the concentration of B is going to decrease. Okay, but Kc always remains the same unless you change temperature. Very standard type of question, but like I kept saying, I emphasized this quite a bit in my previous video, it's about the understanding. It's not about so much about the wording is important, but if you don't understand what we just talked about, I strongly recommend you go back to the previous video, or leave a comments in the video, or if you're from my school, just get hold of me, then I can explain more of that later. Okay, now let's look at B. Number 2. So equilibrium, same thing. Now the equilibrium was colder, so we have less temperature. What's the concentration effect on, what's the effect on B? Now just this first two questions always look at B, it doesn't have to look at B, could look at A, could look at C, could be any one of them, so you need to understand what the heck we're actually trying to do here. So the equilibrium means it's colder, so you don't look at the answers yet, don't cheat. So if this is colder means how does the equilibrium minimize the change? So if you think about it, if the environment got colder, how do they counteract that? So they want to so these guys want to release heat to minimize the change. They want to give the environment more heat, so the temperature goes back up. So they favor the releasing heat process, which is exothermic. So the forward reaction is exo, so you're going to favor the forward reaction. Okay, so here we go. So it's colder, so the equilibrium position has changed, so the system acts to increase the temperature. So if you're reducing temperature, they want to increase temperature. Okay, how do they do that? By doing exothermic reaction, and therefore the forward reaction is exothermic because it's negative here, and this makes more products. So how do you make more products? I need to use A and B to make more products, so B decreases. Okay, so mathematically, if you think about this, Kc is calculated using products divided by reactants. Now we decided we are going to make more products, so this number is going to go up, this number is going to go down, and if you're mathematically savvy, you're going to quickly see that a bigger number divided by a smaller number, Kc is going to increase. Okay, so here you go. So value of Kc increases because you have a high concentration of products, lower concentration reactant, and Kc is going to go up in this particular case. Okay, so Kc values are temperature dependent, so they will fluctuate depending on different temperature. Because if you're playing with different temperature, you are playing with a different, I always use, because I play football, it's a different ball game. Like it's just different, right? Because you're dealing with different amounts of energy, and that will change the equilibrium system. Okay, all right. Next one. So number 3. So what are we doing here? The pressure of the system was decreased. So if we try to minimize, so what's the effect on B? So if we are decreasing pressure, that means we want to favor the side that minimizes the change. We want to favor the reaction that minimizes the change. So if you are decreasing pressure, that means you want to make more particles to increase pressure. Because what is pressure again? Again, refer back to the first video if you the previous video if you didn't get this one. Pressure is about the amount of force the particles have on this on the surface. So if there's less pressure, how do we counteract that? By having more people in the room so they can bang onto the windows, onto the doors. Okay, so the system had to increase pressure to re-establish. So they want to increase pressure. How do they do that? They want to make more gas particles. Okay, so if we look on the left hand side, this is 1 mole, this is 1 mole, this is 2 moles of gas, this is 1 mole of gas, so this is more moles of gas particles. Okay, so as you can see, the reactant side has greater molar quantity, so the backwards reaction is favored. You make more in B, A and B, so B gets greater, and then Kc doesn't change. Okay, so this is the wording. This is obviously very academic in terms of how they wrote it. I probably wouldn't even write like that. So as long as you understand what is happening, how does the system minimize the change, which side would it shift, why would it shift that way, and what does that do in terms of the concentration of the species of interest, and then you're good as gold. Okay, last one. Once equilibrium was established, a catalyst is added. All right, so whenever you see a catalyst is added, just don't bother. Catalyst doesn't do anything. All right, you will only make it go faster. And if the equilibrium has already been established, then it doesn't do anything. If the equilibrium hasn't been established, you will just speed up the process until equilibrium has been established. Okay, so it doesn't do anything else once a system is already at equilibrium. So that's like a free question there. Okay, so that's the Le Chatelier's principle. Let's just put everything in practice. Let's just see how well we done for the first two concepts before we move on to acids and bases in a couple of days. Okay, because acids and bases is the foundation for level 3 aqueous. Because if you suck at that, if you suck at this, you're not going to do so well in the level 3 topic later on. Okay, so let's look at this. So this is the Haber process. I've mentioned this before. That should really be drawn with the equilibrium sign. Let's then explain the role of iron in this reaction. Now you're going to be like, the addition of a small amount of iron will make it help us speed up. It's like, it's so random. It doesn't even, it doesn't even look like it's part of the reaction. So straight away, this means you have a catalyst. Okay. In your answer, you should refer to activation energy and collision theory. So I'm not going to type the answers down here. So just remember that the iron is added to act as a catalyst. It speeds up the rates of reaction because it provides an alternative pathway for the reaction with a lower activation energy. Therefore, more of these particles will have sufficient amount of energy when they collide to overcome the activation energy. So there is a higher frequency of effective collision per unit, higher frequency of effective collision. So if you want to write that down, just play that again and just write it down. My handwriting is too horrible. I'm not going to write all of that on screen. So if you think about it, if this is an exothermic reaction, I think, does it say it's an exothermic reaction? It doesn't. All right. So this is the activation energy. This is the original activation energy. And then when you do a catalyst, this is the new activation energy with a catalyst. So that's obviously going to speed it up. Okay. So this is the reactants. This is the products, and you can, pretty straightforward. Next one. Now it's an equilibrium, right? The Kc. So Kc, this is going to be the products. Remember, when they have a coefficient, the big number at the front, that becomes a power. And please don't, one particular year, I've seen a lot of people adding the products, adding the reactants. It's not this here, this is multiply. This is not this is not add, all right? It's not add, this is multiply. This is correct, all right? Don't go, oh, you told me this is wrong. This is fine. But when you multiply them together, it's the products divided by the reactants multiplied together, okay? Right, the equilibrium, we've done that. Next one. The value is Kc at 640. Show by calculation using blah 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 whether or not the reaction is at equilibrium. Okay, so we figured out before where's our Kc expression. So here we want to know Kc equals NH32 divided by N2 H2 3. Okay, so we're just gonna crunch your numbers. If you can't do this, if you know how to write the Kc expression, but you can't do math, that's really, really disappointing, because I feel like you're being punished for a mistake from another subject, but not for chemistry. Okay, so Kc 677 is supposed to be 640. Is 6677 is at equilibrium? No. Why? Kc is too high. Okay, so if it's at equilibrium, Kc should be exactly the same. All right. Next one. All right. Now this is a question that if you watched my if you haven't got to watch my what do you call it, 2018-2019 exam videos, this is going to be the first time you're going to see this. This is the type of question that I really like. Okay. Because this is the equilibrium, you can copy and paste it down from the, I'm just going to rewrite it because we're going to need this. This is the best type of question. I actually really like this type of question, and this is a guaranteed excellence, and it shows up every single year. So this is a test to see if you actually understood. Okay, so let's have a look. So as temperature increases, the value of Kc decreases. Okay, so temperature increases, Kc decreases. Justify whether the formation of NH3 is an endothermic or exothermic. So it's simply asking you, delta H, is this positive or negative? And you may go, what the heck is that asking me to do? That seems so difficult. I'm just going to give up. Don't give up. It's actually really, really straightforward. This is just connecting everything that you've done for the past for our school, is for the past couple of weeks. Okay, so as the temperature, let's just break it down. Temperature increases. Yeah, this is from the question. Kc decreases. Let's just break it down. All right, let's just write it down and think about what it does. Let's start from the top one. Let's start from here. Temperature increases. This goes back to the Le Chatelier principle. When you have an equilibrium system, when you increase temperature, how does the system react? The system will favor endothermic. And again, if you're confused, like why is this? Detailed explanation in my previous video. So why is this a favor endothermic? Is because you're giving the system more energy. They don't like it. They are going to get rid of it. How do they get rid of it? They're going to suck it into their system. So they use endothermic reaction, which absorbs all of the actual heat energy. Okay, so we'll favor endothermic. All right, so that's the first step. Now let's come back here. Kc decreases. What does Kc represent again? Kc is a ratio of products divided by reactants. Kc decreases. The number has become smaller. That means the products must have decreased and the reactants must have increased. So a smaller number divided by a bigger number must have given me a smaller outcome. So that means we have less products, we have more reactants, because that's how it mathematically will work out. Okay, so if we have less products and more reactants, doesn't that tell me that the reverse reaction is favored? Yeah, because if you're increasing the temperature, you're producing less products, you're making more reactants, so you're favoring the reverse reaction. Okay, so let's just combine them together. The reverse reaction is favored. When temperature increases, system will favor endothermic. Combine these two together, that means reverse reaction, reverse is endothermic. And what are they asking you? The formation of NH3, which is the forward reaction, is going to be it's going to be exothermic. because the reverse fraction in those there for the full fraction is XO. And if you got that, you can expect to get an excellence. Oh, well, I'm not writing all the answers down because these are past exam questions. You can find tons of that on the NCEA websites. You can even find the past 2 years, not 2020 yet, but you can find 2018, 2019 exams on my YouTube channel. But it's just the thought process. Do you understand what Kc stands for? Do you understand what happens when temperature increases? Like which way does the system shift? Do you understand what happens when the Kc changes? And can you combine the two together to solve a question like this? Okay, so hopefully you find this question, this particular video helpful. But like I said, very, very typical type of question. You need to understand your rate reaction, your Le Chatelier's principle, Kc calculations, and put them together, and then you can get an excellence for this question. Okay, so hopefully that's been helpful. So this, if you wonder where this question came from, this is from the 2017 exam. Go on to the NCEA websites if you want like a proper, thorough answers. This is mainly just for I'm just doing mainly for my class. Just read it, make sure you get it, and then we practice it when we get out of lockdown. Okay, so all the best, and hope everything's well, and I'll see you guys next time. Bye bye.